Hello and welcome to the first lesson of our Intro to Rust course. During this lesson, we are going to be installing Rust so that we can use it for the rest of the course. It is a hands-on course and therefore you will need to get it installed. That said, technically you can practice and try Rust out by going to play.rustlang.org and just fiddling around in the text editor that appears. So, for example, if I add this loop here and say for x in 0 to 5, let's print out whatever x is. Don't worry, I will go into more detail about how the actual code works. This is just to show you that we have a demo area. So if I click run on this now, it's going to go through this code and output the hello everybody from the top line and then the numbers 0 to 4. So this is a place where you can try out Rust. But if you want to start doing any serious coding, you're going to want to install it. So in order to do that, the best way is to use a program called RustUp, which you can install from rustup.rs. If you're using Linux or anything Unix-like, you can just copy and paste this line into your terminal. If you're using Windows, just click around and there is an exe for you to download instead. And the program RustUp will basically manage the downloading of every part of the Rust system that you need. So all we need to do is just copy and paste that line into our terminal. Curl is just download it and then just run it in the shell basically. And then you can choose which option you want. I actually already have RustUp installed, but it's pretty straightforward here. So you can follow through the options and get it installed. And then once you have it installed, you do RustUp install and then stable for the stable version of Rust. It will download Cargo, which basically links all your programs and puts everything in the right place so that you can compile it. It will download the compiler and various different versions of the compiler if you want and update them for you. So RustUp is a really useful program. There are actually 3 versions of the Rust compiler you can download. There is stable, there is beta, and there is nightly. Nightly is literally updated every single night, so if you want to keep using nightly, you will do that, but because it's nightly, it's often changing. There's a lot more things going on with new features being added and maybe removed if people decide that they actually don't like the way they work. So it's not. So for now, I'm going to recommend we go with downloading and installing the stable version. But you could try RustUp install nightly, and that will make that available to you. Once that is done, at any point, you could try instead to do RustUp update. Make sure that we're using the latest version of Rust. There's a new version of the stable compiler released every 6 weeks. It is every 6 weeks. The advantage of this from the developer's perspective is that if a feature isn't ready, then they've only got to wait another 6 weeks for the next release cycle to be able to include that feature in the next one. Actually, it seems to work quite nicely. And with a program like RustUp to make sure you're using the most up-to-date version, it's really quite painless. So once that's installed, we need to choose a folder where we're going to be putting our Rust programs. I'm going to put them in scripts, eduonix, and we'll create a folder for our Rust intro. Now RustUp will have installed a program for you called Cargo. So I'm going to run Cargo new to create a new project called V1 Hello, Video 1 Hello, and this will automatically produce some files for us. The first thing it produces is a cargo.toml file. The cargo.toml is basically like the description of your project and all of its dependencies. It's written in the toml format, which basically means a lot of square brackets and a couple of equals. So the name is V1 Hello, and if you want to include any dependencies underneath the square bracket, just name the dependency and give its version, or some other means of importing it. You can give it a path to a local file or a git link as well, and then gives you the source main file, the source files, and then the main.rs, which will be the entry point to your program. And inside that there is a function main. Fn is short for function, and inside here you can change the code and make it do what you want. So I'm just going to do exactly the same as I did for x in 0 to 5. We'll print out what x is. Don't worry too much about the exact code. It's more about just making sure that this works so that you can get something installed. At least if you can get it to print hello all of you, that will be a perfect start to knowing that the compiler actually works. And I'm going to tell you a bit about my workflow here. So what I'm going to do is I'm going to have one window open running Vim, where I'm going to be editing the code. Don't worry about which text editor you use. If you're not already familiar with Vim, I don't recommend you start on that at the same time as learning a new language. There are plenty of good text editors. Make sure the text editor you get has good syntax highlighting and ideally can point out errors for you. With those two features, you should be well set to get programming in Rust. Then what I'm going to do is I'm going to have another window open with a terminal, and I'm going to use this one to actually run the tests and compile the code. So we just have the two windows, one above the other, and I'll just hop between them to run the tests. So I'll just move into the correct folder, the same folder as we have been working in. So scripts, edunix, Rust intro, v1 hello. And then when I call cargo run from here, cargo is a program that manages the compiler. And then here we go, we've outprinted hello all of you and all the numbers from 0 to 4, as you would expect when printing a for loop from 0 to 5, right? It doesn't include the last number. A couple of other things I want to show you. There is a website called crates.io. On this website there is a bunch of packages where you can download them and include. It tells you about the various packages that are available and easy to include in your project. And then there is of course docs.rs. I do find it quite funny that everything uses the .rs. I looked up the domain end and it represents Serbia, I think. So it's just kind of funny, but rs is short for Rust, so that works. So yeah, you can go to the docs.rs and you can find out anything you need about any of the libraries you're using. Just follow the document links and click through and see what they want to tell you about how to use various parts of the system. So that should be enough to get us started. In the next video, I'm going to be introducing the structs and the ways we can build our data types in Rust and then combine them to actually make a program work. I will see you there. Hello and welcome to the next lesson in our Intro to Rust course. During this lesson, we are going to be looking at Rust's data types, starting with the primitives and then moving on to slightly more complex data structures. So I've created a new project here using cargo new. And so inside this project, let's just start creating some data variables. So I can do x and I can give it a type behind a colon. So x colon i32, that's an integer with 32 bits. Set it to a number and I can just print line on that number. And then when I run it, I get 3. So the print line I should go through, that is slightly different to, I guess, a function that you might be used to. It's actually a macro. And it happens at compile time to build out this structure into something that will print the x very efficiently. You can write to standard out yourself, but this works quite nicely. If you're just going to be printing out, it is what most people use. So what's happening inside the string that's got the curly braces, it's kind of like a format string, so you can write anything you want, and anytime you use those curly braces, a pair of curly braces, that will be replaced by the variables to the right hand side after the comma. So that curly braces will be replaced by what is in x. If we had another curly brace and another variable, that would also be replaced by the next variable. There are a bunch of other formatting options. We'll come across those a bit later in the course. So now we have x and we can just make it a different type. We actually don't need to give it a type. If we don't write the type, this still will compile and it will just guess what type based on the information it's got, like you're sending it to a function which requires an i64, in which case it will guess it's an i64. Or we can use bool if we want booleans, right? So if we set bool, if we set x to false, or even 3 is bigger than 7, that will work. 3 is bigger than 7 resolves to a boolean, and that prints out false. So all of the standard operators exist in Rust. You don't have to think, okay, which ones can I use? So we've got bigger than, less than, etc. Exclamation mark for not, star for times. So, and then for your integers, you've also got i8, i16, and then the last one is isize, which is an integer of the same size as the pointers on your system. I think it actually goes up to 128. You can get an i128. That's an integer made of 128 bits for when you need those big numbers. And for every one of those, there's an unsigned equivalent. But a usize will be the same size as a pointer I'm you can kind of convert between them if you are feeling that way. And then we've got bool, and then we've got str, which I'll talk about more later, but it is a primitive type. You kind of describe those, that's just letters inside quotes. To get on to more complicated data types, we're going to talk about what a struct is now. Now, basically, a struct is a way of organizing data into groups with each part being named. So I'm going to build here a public for struct, and this is a point. So public means it's available outside this code file. Struct says that it is a structure of data, and then point says, well, it gives it the name. In Rust, to give a type, we use a capitalized kind of camel case. So you use capitals and lower cases to delimitate the new words. The parts are defined with the name, colon, type, comma. And you can list as many types as you like or parts as you like. In this case, a point just needs an X and a Y to refer to a location. And then we're going to have another struct here, which is a ship, and this has a location, and that location is a point. So now that we've defined point, we can use it wherever we like. And we'll also have the status of the ship. Now, what should a ship status be? Well, let's define a new type, and let's call it ship status. So I want you to imagine for this kind of project that we're building a bit of a game and that we've got some ships that need to move around the board in some manner. So this ship's status will be, it could be engaged, it could be involved in some kind of fight, it could be waiting, not doing anything. It could be firing, it could be trying to shoot at a target. If it's got a target to shoot at, then that will be a point. And this is the feature of enums in Rust that I really like the most. You can give one member of the enum the data it needs to work. So if we have a heading, that is a point. But if it's engaged, there's no point available. But we don't need to set it, and we can completely ignore it because it just doesn't exist if we're just engaged or waiting. So that's pub enum. An enum just basically means an enumerated type, so it's kind of like a choice between it's going to be in exactly one of these states. If you have something that is an enum, it is going to be one of those modes. So we'll make a new ship, so in our main function we'll make a new ship. Let's call let mute ship. So the mute means we're going to change it at some point in our code. It's a ship, and we'll create this ship using the kind of description of each part. So the name of the ship, inside wiggly braces we give each part, and then the value we want to give it behind a colon. So that's location, and then colon. Capital point means we're going to make a new point, and we'll just fill that in the same way using the squiggly braces. So X is 10, Y is 10, and then we'll fill its status, and again to fill it the ship status we'll say it's a ship status waiting. So now we know for sure that this ship is in waiting mode, and actually that makes our code very easy to read and reason about, because we know exactly what mode our ship is in. And if we want to add new modes for the ship, it's easy. You just add them to the enum, and it keeps the code really easy to read. I've also got Rust Thumped running every time I save my code, so that's why it sometimes jumps around. You should absolutely use Rust Thumped. Make sure your system is set up to when you use Rust Thumped. Most text editors will do something like this, but if not, you can always just run Rust Thumped from the command line on your files, and it will go through them and format them nicely. So now that we have our ship and its location is set, we can just change its location trivially with ship.location.x, for example. We can change its x position. We'll add 10 to it. So plus equals means add in place. And then we can print line our ship's location. Like I said, it's a formatted string. So we use the wiggly braces to represent the two things. And here we go, outputted, ship location equals 2010. And it's saying here we never read the status, so why do we bother including a status if we're never going to read it? We'll fix that shortly, but for now I just want to show you what mute does. So if I get rid of this mute and try and run the code, actually the compiler is going to complain because we're trying to change something that we don't have permission to change. Unless we declare something as changeable, we can't change it. That makes sense, and it is helpful. It gives you a certain level of protection against accidentally doing things that you're not supposed to do. So you need to say, oh no, I do intend for this variable to be changing throughout the course of this program. Often you just want a variable to be filled with something and then just use it afterwards, never needing to change it. And making sure that something isn't mute gives you an extra moment to think about whether or not you want it to change, or if you've made a mistake in your plan. Now, what I'm going to do here is a little bit of macro magic. Macros in Rust they're not too complicated, and you can write a macro that does these things for yourself, but we're not going to be covering macros during this course. I hope to do another course later where we go into more detail about how these macros work. But when I write derive debug or derive partial EQ like this with a hash and square brackets around, what this does is it kind of adds code underneath your code. So if I've got my pub struct ship here, basically underneath ship and before ship status, the compiler imagines there is a bunch of other code that implements the debug trait. Don't worry, we'll come to traits later, and the partial equality trait just underneath. And it does that by reading the code that I've written and going, oh, that's that. I need to put one of these and one of these. It's really handy, but it's a little bit complicated for the first lesson. So all I really want to show you is that by writing this, it makes debug available. That means we can call this function called debug or print it in a debug way, and it will give us all of the internal data of an object so that we can easily read it and debug our code. It's really useful, and I'll show you what that does when we do a print line here. So here we can do print ship equals, and then instead of just using a normal squiggly brace, close squiggly brace, we put colon question mark. That means print its debug form. So if I print out the ship here, it now gets our location and point, and it tells us that its status is waiting. So that's a lot of useful information to get just by writing that derive debug. That just makes things a little bit simpler for us to check through our code. If you want to print it out slightly more nicely, you want to implement another thing called display. I'm not going to go into that right now. But it is worth noting that now that we've implemented debug, because that tells the compiler we are actually going to read from status, so now it's not complaining that status is never used. So that's basically how we can structure our data in Rust. There are some other tricks that we'll come to as we're going on the course. But in the next lesson, I'm going to be adding some functions to our data types so that we can kind of automate things and make things easier for other people to use the code. I'll see you there. Hello and welcome to the next video in our Intro to Rust course. During this video, we are going to be adding functionality to our data types. So each data type sometimes needs to be able to manage some specific behavior of its own, and it's helpful to think of it as part of that type. So in this lesson, I'm going to show you how we do that using the keyword impl. So as you can see, I've opened up the file we were working with for the last lesson, and we're just going to add some functionality to it. Let's start here, and we'll just write the keyword impl and then point. This says 4 points, give them this implementation. And actually, this is quite a nice way of doing things because it separates the shape of the data structure from the code implementations. Meaning it's much easier to read what the data structure actually looks like and how it handles its contents than having it all together. And there are reasons that that's helpful, which we'll come to when we start talking about traits. So for now, we've got our impl on point, and we're going to create a new public function, or a public function new, and it's going to return self. So the keyword self here is pretty important. Capital S self refers to the type at the top of the impl. So in this case, self means point. And it's going to take some values that will help us construct our type. It's worth noting that it doesn't take a self object, it creates it, right? So we're going to create a new point here. We're going to use x is x and y is y, and we can just return that value. But actually, because x and x are the same thing, there is a little feature in the Rust compiler that allows you, if the name of the variable you want to put into a struct is the same as the struct's property, then you can just write the name of the struct's property. So this will put the x in the x and the y in the y. It's actually slightly more readable, and it's slightly shorter. That's what I find doing things this way. It also encourages you to use the same variable name as the struct type when writing the code. Let's give it another function. Now this is going to take and self, so it's going to take the struct we're working on, and it's going to take a pointer to another point, and it's going to return a point. Actually, let's make this transpose, not add. So if we've got one point and we want to move it by the same length of another point, so that's basically the same as add, but what we're going to do is we're going to move this point. So instead of taking a pointer, which is what the and represents, we're going to take a mutable pointer. That means we got a reference to this object that we are allowed to change. So if someone sends us, and self will be the object it's called on, but I'll show you when we're calling it what that means. Self.x plus equals p.x and self.y plus equals p.y. So this adds the two parts of the points together into the self object. So now we'll build an impl for ship as well. This one will be attack. So it's going to move our ship into attack mode. It's going to attack a specific point, perhaps on the map. So it's going to take a point, and that's not a pointer because we're just going to stick that point right into the attack mode, the firing mode, as it were. So self.status equals ship status firing, and that's point P. And that should be two colons there. The two colons kind of represent go inside, right? It's like when you're working with types and modules, that means go inside. When you're working with an actual data structure and you want to read parts, you use dots. So we've just set the status to firing. So now here we're going to demonstrate how all of this works. Let's make a new point, and it's a mutable point because we've put let mute a equal point, and we'll give it a value. So a capital P colon colon, that means it's a class method new. So the method new belongs to the class. We wrote it ourselves. It doesn't have a variable to work with, so we just use the class method and call it with 10 and 4 just to give it some position. We'll make another one. It's exactly the same, 20 minus 4. So it's got slightly different position, but other than that, it is a point, and it's just that easy to make a point. And then we can transpose A with a pointer to B. So even though we don't specifically say pointer to A, because we're calling it's becoming self, it kind of does the math to work out what A is going to be sent, and it just automatically makes that work for you. So it's a pointer to A and a pointer to B. If we get rid of the mutability, because it knows that it needs to be a mutable pointer to self, it takes in the function, transpose takes and mute self. It says, no, we can't borrow A as mutable, which is what we need to do to be able to call transpose. So we make it mutable, and then when we call transpose, again, like I said, this mute keyword protects us from certain mistakes, because we might forget that transpose actually changes the object and call it on something we need to stay the same, whereas having that mute keyword guarantees that we're not going to accidentally call something mutating something that we don't want to change. So now what I'm going to do is I'm going to write an assert equal on A and see that is it equal to 30, 0, which it should be, right? 10 plus 20 is 30, 4 minus 4 is 0. So what that's going to do is basically it's going to panic if these 2 points are not equal, and it uses that partial EQ thing that I derived at the top. So I derived debug and partial EQ. Partial equality means that these two things can be compared using the double equals operator. So what it's going to do is when we try and assert that two things are equal, is it's going to basically go check whether these things are equal, and then if the two things are not equal, the code is going to just stop there. It's going to panic and go and break out of the program and print an error message as it leaves. Panicking can be really useful for situations where you are pretty sure this should never happen, but if it does happen, we've got a problem in our code. That's kind of where you want to use panicking. So like in this situation, we've literally defined every single part. So if these things are not true, then this should break. Whereas if the error is
in the outside world, maybe a file is missing or something, that's when you want to return an error result and pass that around appropriately. And let's also write ship attack B. So we're going to get that point that is B, and we're just going to give it to our ship to attack it. And let's just get a description of what our attacking ship looks like. Just by using a print line. So our original ship was in the status waiting, and then we called attack on that ship, which changed the ship. It kept its point the same, its actual location, and it set its firing point to what point B was. That was 20 minus 4. So that has basically worked. We've now managed to add functionality to our types, and so now we've got a definition of types that we can add together. That's functionality added to our types in a fairly straightforward and readable way. And now we can, and in the next lesson I want to talk about matching. We have these enums and how we can get specific parts of enums and read them correctly using patterns. I'll see you there. Hello and welcome to the next video in our Intro to Rust course. During this video we're going to be looking at patterns and how we can use matching on them to find what part of an enum we need to refer to and reference its internal data. So to do this, we're going to continue with our previous project, and we're going to add a time step method to our ship type. So this is when time passes, what will this ship do? And so we'll just call it time step, and we'll take a mute self, and we will take some kind of pointer to a world. In this case we'll go with a vec of action. A vec is basically a list, and it's of actions. So the angle braces say it's kind of that type. And we will define an action, and for this action it's going to have a shot mode. And actually when you're working with enums, oh yeah, this is an enum, I'll fix that in a second. When you're working with enums, you can use squiggly braces to name the constituent parts of the enum, like you used the brackets and just gave the parts like point in firing and heading. If you use squiggly braces, you can actually name them, which means you can access them by name when you need to later. So we'll have a shot, which is from and at, and we'll have a move, which is from and to. We'll fix that to an enum, and we'll make sure it's got debug and partial equality. So now for our time step method. We'll start with a match on self.status. So basically match takes a number of patterns, descriptions of what could be in the data, and with some variables in that it can maybe fill, and tries to fill those variables, tries to make that match what is given in the variable that it's matching against. Then performs the commands in the first case that it can match against. For example, the status heading with a point, we should do a move from one place to another. And so the P in this case becomes that point that we referred to in our heading enum type. And so now we can, maybe we'll have to calculate what our new position is going to be. And we're just going to move one space towards our current heading in both X and Y. It's not perfect, but it will do for the function of this game. So we're going to say the new X, or NX, is going to be, and we're going to use a match statement here as well, because what we can do with match statements is we can actually assign the result of a match statement to a variable, and the match statement will be it will choose the result from whichever branch it matched on and just put that into the resulting variable. So in this case we are comparing the new positions X with our current X, and we're going to use comp, and that will return an ordering. Standard comp ordering, and so we can match on that ordering enum. So in order to use something from the standard library, it's standard : and then whichever module, and then : and then whatever you want. So colons allow you to go into modules, as I kind of described before, and if you use star, that means grab everything from it. So greater here is from that standard comp ordering. So if our result is greater, add 1. And we're doing that, and this works because ints implement a trait called ordering, we get less, in which case we'll take one away if the target point is less than our current position, and we'll get equal. Just like with our functions, it's just the return type of the match is the return type of all three of its branches, and all three return types must match because they've got to go into the same variable. That should be ship status there. Now this says here we've got non-exhaustive patterns, engaged, waiting, and firing not covered. So obviously our ship status has 4 possible options. We'll need to cover those in a minute, but for now we still need to get our Y position. And I'll just use a bit of Vim magic to switch all those X's for Y's. So now we have our new position for X and for Y. So now we can add that to the move list by using the word push, the function push. And we're going to push an action called move, and its from is our current location, and we have to clone that because we are taking it from because we want to keep access to it inside our location, and we're just making a new point with NX and NY. And the actual NX and NY don't ever need cloning because integers implement this thing called copy, which means that they will be copied rather than referenced anyway. But in order for our point to be clonable, we actually need to derive clone for it. So I'm just going to add that to the derives. Implementing clone means I can call clone, and that will do a deep copy of the object. So that will clone everything inside the object into a new object. So it's time to deal with that non-exhaustive match statement problem. And what we'll do to solve that is we'll create a match everything case. And this would just be a variable of some kind we could do. But if we just use an underscore, that means we don't care about this variable. And then when we get there, we'll just open squiggly brace, close squiggly brace to say we're not going to do anything for the other cases. So as we come back to self.status, you'll see there's another error which is saying we're trying to take stuff out of something we're borrowing. So we've borrowed mute self, and at match self.status it's saying, well, we're taking it out because we need to get the variables out of the enum. So what I'm going to do instead of matching against self.status, I'm going to match against a borrow of self.status. I'm going to take a pointer to it. And that means all the variables that we get out will also be pointers. So instead of P being an actual object, it now becomes a pointer to an object. And that actually fixes everything we need because we didn't really want to be copying too much anyway. And we absolutely have to clone the location. We can't, we can't take something out of the time step. We'll go to this in more detail when we start talking about lifetimes, but basically when you use some part of some object, you just can't use it again unless you've only borrowed it and given it back. This is one of the areas of Rust that takes some getting used to. It is the most different part of Rust, but the whole next chapter is going to be dedicated to lifetimes and memory and understanding that, so don't worry about it too much for now. So, and then we're going to put our self location is the new location, and that does everything for that. So what if our ship status is firing? Well, then again, we'll have another point to handle. And in this case, we'll just make a shot. So we'll add it into the array. So v.push, and then we'll do an action shot. Shot is defined with a squiggly brace. Its from location will be our current location. And again, we'll have to clone that. And its new location will be the point we're firing at, and we'll have to clone that. Got to get the brackets in the right places, and then that sorts out the layout for us. In the other two cases, we're not going to do anything, but that should show you what you can do with match, or at least some of what you can do with match is how you can just break apart enums. But let's actually get this tested. Let's just make sure that it works. So we'll have a new vec of actions, and we'll set that to just a new empty vec. So, and with this vec, and then we'll call time step on our current ship, and see what it does. Obviously we need to mutate actions, so we need to add the mute there. And then we'll just print out what our actions are now, just to see what has been added to our action list. So cargo run, and there we go. Our actions is, you see the square braces means that's a list with one element there, and the element is a shot from point 2010 to 20 minus 4, which is what we want. But we can do other things with the patterns as well. Like, I mean, if we just simply do let x comma y equals and then define a tuple is just it's like a structure, but none of the parts are named, and you put it in round brackets. In this case, we'll do 34 comma 55. So we've defined a tuple on the left hand side, and we want to assign that to the variables on the right hand side. Because of pattern matching, basically what Rust is doing is it will just break apart that tuple, which is again just it's like a struct, but none of the parts are named, into this tuple on the left hand side, putting the 34 in the x and the 55 in the y. So that is, again, it's using a pattern. So patterns are literally everywhere in Rust. Every time you see an assignment, the left hand side is a pattern. Sometimes that pattern is just the variable name. And you can also do a check on that as well. So if we do if let ship status, and we'll go with firing, is equal to ship dot status, then if the ship status is firing, then x will become the point that it's firing at. Otherwise, it just won't enter this block. So there's no risk of you trying to read a variable that doesn't exist. These enums really protect you from trying to access something that doesn't make sense to exist in this situation, because you just can't read the variable. So there we go. Because the ship status is firing, it does enter that block and it is able to print that section. So that is everything I need to tell you about match patterns for now. In the next video, we will be looking at loops and iterators, and I will see you. Hello and welcome to the next video in our Intro to Rust course. During this video, we are going to be looking at loops, how we can write loops, and how we can use iterators to facilitate building our loops more easily. And so again, I've already created a new project, and we're going to start by importing standard env args. Now, standard env args is basically the module that's going to allow you to access the command line arguments that were sent to the program when it started. We just use the args, which is a function that will return an iterator. So we can go for x in args, and then we can print line hello x. Now x will be a string, so that's just a set of letters. And when we cargo run, we can use double dash because cargo has its own way of taking arguments. So, but everything after the double dash is sent to the program directly. So Dave will be the first argument we sent to the program. So as you can see, when I run this, we get hello, and then the first argument is the name of the program, v5 loops in a path. The second argument, third argument, and fourth argument are the command line parameters that we gave here, Dave, Pete, and me. So there we go. Now we have a way of getting input from the user with very little effort. We just read through all of the arguments and just act on those. So now as well, we can loop through other things too. We got 4x in, and then we do 0.10. Now 0.10 creates what is referred to as a range object, which is of course an iterator, and so we can print out all of the values inside that range. Note that it doesn't reach 10, it stops 1 before. This is standard in programming languages, because if you have a list that has 10 elements, the first element is 0, the last element is 9, so this works well for general looping to have the range not inclusive. If you really want it to include the last number, you can use ... equals, and that will include that final number. Okay, so we'll try another thing here. We're going to create another range object for kv in 10 dot dot 20, and we'll put those in brackets, and we're going to call enumerate. So enumerate is going to create another iterator and wrap it around the iterator you give it. And then when it reads the result of the first iterator, it will attach a number to that result and return them together as a tuple. Now, that sounds fairly complicated, but it's really straightforward. Basically, by calling enumerate, we get the number in the loop of each element. And we'll print out k is and give the value, and v is and give the value. And then when we run our program, we have k equals 0, v equals 10, k equals 1, v equals 11. So you see we've got the number, the key, and the value. This is really useful for all kinds of things. So just making sure you're in the right place while reading through code. So the next thing we're going to do is we're going to create our own iterator type. And for this one, we're going to do the Fibonacci number. So Fibonacci as a sequence starts with 1, 1, and then adds the last two numbers to create the next number. So 1 plus 1 is 2, and 1 plus 2 is 3, 2 plus 3 is 5, and so on and so forth. So we'll create a pub struct fib iter, and to make a Fibonacci iterator, we really need to track the last two numbers to make sure we're adding them correctly. So we're going to impl the trait called iterator for our fib iter. So this trait iterator is how Rust does for loops, and it's getting your head around traits is a very valuable feature in Rust, so I'll spend a bit of time on that. A trait is basically an interface. It's a way of interacting with a different kind of type. You don't know what the type is, you don't know how it works, but you do know that it has at least these methods or this functionality. So for example, the iterator trait has two important features. It has a type that's associated to it, and it has a function called next. Let's have a look at what an iterator actually looks like. So we'll show the declaration. So the public trait iterator, it has a type called item, and it has a next method which takes a mutable self, and it has to be mutable because you need to go on to the next result. If it can't change, it doesn't know that it's got a next number to get to. And that returns an option. There is an enum which can either be sum, and it's of that value, that item, or it can be none, in which case there is nothing to read, and that means the iterator has finished. So that's everything you must implement to make an iterator. You can actually override all of the other functions as well, but they are provided. So you don't need to worry too much about the rest of the functions defined here. They are all provided if you want them. So for example, our iterator, its item will be type i32, so our next function must return an option of i32. And then we do just a little bit of the weird maths inside here to make that work. So we'll do c equals self.a plus self.b. So the next value is of course the previous two values added together. We'll move b down one space to a, and then we'll put c in b, and we'll return that option sum of self.a. But of course, if you get to the point where you've run out of elements, that's when you switch it and you return none to let whoever's using it know that you're finished. We're not going to do that in this case. Let's also implement a constructor for our fib iter, so a new function, and we'll put that in a separate impl because this isn't implementing something else. When you're implementing a trait, you have to only implement the functions available for that trait. So if you just want to implement something else, you have to put it in a separate impl altogether. So now let's loop through our fib iter, and we'll just take the first 15 values from it. So again, take is a wrapper. It wraps your iterator in another iterator, and once you get to the nth element, it just returns none. So that means you know you're going to get exactly 15 elements from your iterator. And of course we'll print that. Oh, and that should be a capital fib iter new. That's the constructor. And there we go, 1, 1, 2, 3, 5, 8, 13, 21. That looks like a Fibonacci sequence to me. Okay, actually it's starting to annoy me that we keep getting the hello to the name of the function at the top here. So what I'm going to do is I'm going to call skip1 on the args iterator, and basically what that's going to do is it's going to read the first one element before it makes its first return. So again, there's lots of little tricks for making sure you get the exact numbers you want when you write these iterators. So you see before we have this hello home Matthew, and then we save this, and now when we run it again, at the top, we no longer have this hello Matthew because it skipped the first element and we've not provided it with other members to that list. A for loop is actually what they call syntactic sugar. It makes writing the code slightly simpler, but actually when you try and write it and actually run the code, it kind of turns into something else. And so I'm going to show you what it turns into. So if you understand what it's going to turn into, then it makes it just a little bit easier to, I guess, to write code that's going to act on it. First, it creates the iterator, what let I equal, and then our fib_iter::new.take. So that's what we do, we create the iterator. Technically, it also calls into iter on it, which is dependent on a trait called into iterator, which is automatically implemented by every iterator because they can all become iterators easily. But ignore that for now. And then while let sum v equal I.next. So again, it takes this option and you know how we were using the if lets? Well, now we can use while let. So while we are able to let something equal I.next, we can act on that next value, that v. So this is the same. It's not exactly the same because I've chosen a different take, but it is functionally very similar to the previous one. But let's add an extra feature to it. Let's add a filter. So let's say, for example, we only wanted the even numbers in the Fibonacci sequence. We can do this by using a filter. So we already have our fib_iter, and now we just want to filter them and make sure we only get the even numbers. Filter in the bars, in between the bars, these are the parameters to what is called a closure, which is basically just an unnamed function. That's just a way of writing the definition of a function really simply so you can send it to other functions. So in this case, we're going to write the two bars saying x is the parameter, and we're just going to check if x mod 2 equals 0, and it will just straight up return that x mod 2 equals 0. So modulus 2 means the remainder when divided by 2. If that remainder is 0, the number is even. So we just quickly define this function, and sometimes it's really handy just to be able to write just a one-line function for your check or something, you know. Does this equal that? Does this make that? We'll just send this function to the filter, and then when we run it, we'll get our other fib. It starts with 2, 8, 34. So we've got 10 elements here. So filter did the filtering before the take. So we still got all 10 elements, and they're all the even numbers from the Fibonacci sequence. So that's it for this lesson. So that's it for showing you how for loops work. In the next lesson, we're going to be going into more detail about how generics work. That is the generics being what we did when we had vec of array or option of I32 in those angle braces. That's generics, and we're going to go into it in much more detail during the next lesson. And I will see you there. Hello and welcome to the next video in our Intro to Rust course. During this video, we're going to be looking at generics, which is a tool for reusing the same code across multiple types. So because of that, I'm going to, instead of creating an application program, I'm actually going to create a library, because normally if you want to write code that's going to work across multiple types, it's going to be intended as part of a library. Not always, but quite regularly, and it gives me an excuse to show you how to build a library in Rust. So here we will do cargo new, but instead of just naming it, we'll do --lib to say this is a library. And it does create a folder exactly the same as before. You still got your cargo toml, you still got your source, and it's worth noting as well that it also runs git init for you. So if I do a -a, it shows that in the tree there's a full git setup there. This is not a course on how to use git, but it's worth noting. So we're going to work with our point type, but we're actually going to change our point type to allow it to work on more kinds. So it doesn't have to be a point of I32s. It could be a point of F64s, or it could be even a point of strings. So pub struct point, and this time in angle braces I'm going to put n, which means that the internal type of this point is defined as n, whatever n turns out to be. So in this case that would be x will be of type n and y will be type n. So a point, these could be distances of any kind, but a point just has an x and a y value, and each represents some kind of distance generally in each of those two directions. And of course we're going to derive the usual things, partial equality and debug. And now when we try and impl functionality for our point, we have to say in our impl what types we're using in this impl. So impl angle braces n, and then we're going to impl a point of type n. It's the same n, and that's where we can kind of put any constraints on n. I'll come to that in a second. Now, and so now when we write our function, our pub function new, it's going to take x, which is of type n, not of i32, y, which is of type n, not of i32, and it's going to return self, which is of course a point of type n. But the actual function is pretty straightforward. We just return the point x comma y, and that works. Now the next function, transpose, we will take a pointer to self as usual, a mutable pointer to self, as we're going to move this point in these directions. And we're going to take a p, which will be a pointer to another point of type self, capital S. And this function actually doesn't need to return anything. So what we'll do here is self.x plus equals p.x, and self.y plus equals p.y. So this is exactly the same as our code before, but we've got an interesting problem here. The plus equals operator cannot be applied to type n. So what that's saying is we don't know anything about n. We know nothing. N could be a string, n could be, it could be some other complex type that we've not defined before, and we don't know that it's possible to use plus equals to add these two things together. So we're going to actually add some constraints to type n to make this work. So that constraint is called add assign, and that's standard ops add assign. So we're going to bring in this trait. Add assign is a trait which basically has the method add assign. And by saying that n has this requirement, we now know that we can do add assign with these values. And the next error we're getting is we cannot move p.x out because it's behind a shared reference. So as before, we're going to make sure that clone is available. So we just have to add that clone requirement, and then we can call the clone method on it, because if it implements the clone trait, we get the clone method. So basically, here's what you're getting out of this. You don't know much about the type you're being given in this for this type, but you do know that it implements add assign and that it implements clone. And that means you know that you can perform all of the actions needed to make transpose work. Doesn't matter what type you're getting, as long as that type implements add assign and clone. So what you want to try and do is to keep these requirements as loose as possible. Now, you can't get rid of add assign because we need to be able to add it into, and we can't get rid of clone because we need to be able to copy that value out. But that's it. That's the only two requirements needed for our value to work. And we can actually add these to the type itself, so we can always guarantee that a point will have some kind of add assignable type. Add assign is what allows you to do plus equals. There's mul assign, which allows you to do times equals, etc. as well. But we don't need that. We don't need to know that our type can implement mul assign to be able to run transpose. Now we can actually break our impl into separate parts if we like. So if we don't put the constraints on the type, we can make a new type of type n with no requirements. So we can just make that struct work for type n, and we can have an impl of n where it's add assign and clone. So transpose only works if n implements add assign, but new works in any case. It doesn't care whether n implements anything. So we can actually get different functions available depending on constraints on the inner types of our objects. So you can actually make very generic types which have extra functionality if extra functionality is allowed inside the inner types. Okay, so let's also use standard ops add, which allows the plus operator to work, right? And we will implement add ourselves for these types. And by implementing this, that means we can get the plus operator to work on our types. So we'll start off as before with our impl, and we'll require an n, and the n must of course impl add, because we need to know how to add them together. And it could also do with implementing clone. Actually, that's less of an important thing. So we're going to impl the method add, and that is for point n. So as long as n implements n, add, and clone, we can implement add for point of n. So the add function, which is required of the trait add, requires self and a right-hand side, which is of type self, and we are going to return type self. And so to return, we're going to create a new point where the x is self.x and the right-hand side's x added together, and the y is self.y added with the right-hand side's y. So we add each part of that together. Now we've got a couple of errors here. The first error here is mismatched types. Now this is a little bit odd because you'd think, well, we've got the same type. We're returning a point of type n, which is self. So what is the problem? I'm going to have to cargo run it to show the error more completely. I'm going to have to run cargo test. When you want to run a library, you can't use run because it doesn't have an entry point. But here's the problem. So it expects a type parameter n, but it found an associated type. So an associated type is something that it doesn't know what type is. That is because the add method could return a different type to itself. If you add together two matrices, for example, sometimes you can end up with another matrix of a different size again. There are other cases where sometimes adding two things together creates a different kind of object. So the add trait actually has an associated type to it known as output. So we need to add that, we need to clarify that requirement in our add method too. So we put in angle brackets that the output of the add, the n impls, has to be n, because n is the type that we are adding and hoping to get the same result for. So that gets rid of that error. We still have one more problem. Not all trait items implemented. Exactly the same problem. We haven't declared what our output type is. So that, in this case, that should be self. So if we add together a point of n to another point of n, we should get another point of n. And that clears everything up. We've now implemented our add trait. Now for the sake of I guess completeness, I want to derive clone for our point n. So that's everything we need to know about generics, at least for now. During the next video, we will be learning about writing tests and using that to write the tests for this module. I'll see you there. Hello and welcome to the next video in our Intro to Rust course. During this video, we will be learning to write tests and using this to write tests for our previous module on generics. We've got this keyword here, CFG, which means config, open bracket, test. And the job that does is it says only compile this if we're running tests. Don't compile this if you're actually building the library. And then the hash test, which comes in front of the it works function, that adds a couple of extra things to make sure that it does get run when tests are required. It works function, now you can have as many tests inside of test module as you like, but we'll just carry on working with the it works function. First thing we need to do is we need to use superstar inside the module called test. So actually sometimes we can break our code into modules, and by doing that we get to separate our variables and separate various types in such a way that the outer scope can't access the stuff that's in the inner scope unless we deliberately name the module. It's : this. And the inner scope can only access the outer module. It uses super : star. So we're going to use super : star. That's everything from the module that wraps this module. So we'll start by making a few points. We'll make a new point at 1, 7, a new point at 2, 3, and then we'll just make point 3 will be 0.1 plus 0.2. And then we can assert that P3 is actually equal to another kind of point, which would be at 3, 10, right? So 1 plus 2 is 3, 7 plus 3 is 10. So if we've added these points together successfully, we now have a point at 3, 10. So we'll run the test. So that was cargo test, and we got a result back there saying running the test, it works, and that came back okay.
So remember, the assert equals will fail if these two things are not equal, and then it will panic, and the test panicking is how we know it failed. So if we change the output of our test, if we said it should match to 11, and then we run the test, we actually get a failure, and it tells us exactly where the problem is. It says the point x3, y10 does not equal the point x3, y11. And actually we can add a message to our errors too, with no extra cost. Just stick it on the end and just get a bit more information from our test that fails. So points don't match. There we go. Okay, we'll carry on now and we'll try something else. We'll try p.transpose, and we'll take a new point to transpose, which will be 6, 6. So this should move p2 in that direction. Except p2 cannot be used again because it has already moved. Now, this is because inside the add method, we took self, and the right-hand side was also self. They didn't take pointers, they didn't borrow it. So actually what they do is they consume the variable. The method add consumes the left-hand side and the right-hand side, and you can't use them again. Now that's okay, we do have a solution for that. Either we could derive copy for our point, in which case that will not be a problem, or we can just use clone on p2, and that makes it available. And of course, now we're changing p2, we need to make it mutable. And that test still fails because need to fix that back to 10. So there we go. Now the test has worked. So we had to clone p2 to make it so that we could use it in 2 situations. You can get away with that if you implement copy for it, because then the compiler knows actually this type is so simple, there's no risk in copying it. But the reason we have to choose to use clone or copy is because sometimes they contain pointers to other things. So if a type contained a pointer to something else as part of it, and then you copied it, now you've got 2 things with a pointer to something else. So when you drop the objects, when you free them in memory, you don't know which one should free the memory at the other end. And unlike a lot of modern languages which have a garbage collector and an internal reference counting mechanism, Rust doesn't do that because it wants to be as fast as possible. So it makes sure you use your pointers in a way that is safe. We'll go into that into a lot more detail in the lifetimes chapter. I want to try something else just to show you that 2 points with a pointer of some kind and a pointer of another kind are not the same type. 2 different points, they are considered by the compiler completely separate types because they have different internal types. So to do that, I'm going to make another point that's a point string. Let ps equal point new, and we'll give it 2 strings instead. So this is no problem. Actually, they're static strs. And we're going to assert equal p3 and ps. And then when we run this, we get an error that describes that these 2 types are not the same type. It says, hang on, the right-hand side, I expected that to be a... Hang on there, I expected the type point integer, but it turned out to be a point str. The point on the left is a point integer, it's a point of integers, and the struct on the right is a point of str. They cannot be compared. They are not the same type. Actually, if we really wanted, we could implement partial equality for these 2 types between them, and it would be okay. But normally 2 objects of a different type cannot be compared. During the next lesson, we will be looking at the result type and how we can use it to handle different errors in a way that is consistent and easy to read. I'll see you there. Hello and welcome to the next video in our Intro to Rust course. During this video, we're going to be looking at the Rust result type and how we can use it to return clear and usable errors. I want to show you quickly what the result type looks like. It is part of the standard library, so you do not need to write this code, but it is a pub enum result of type T, and then it's OK of the T, and it's got an error of type E, so we'll add that too. So it's just an enum, like any other enum. If your function returns a result, you can either return OK type T or an error of type E. So your type error must be known when you compile it, but you can make an error of
any type. And often your error type for a function will be an enum describing in some way what happened. But we don't need this code, so I'm just going to hide it behind some comments. So the next thing I want to do, and in most of your libraries you will want to do something like this, you will want to have an error type for that library. So I'm just going to create my error, and this will have options of different kinds of errors. Now, in this case, we're only really going to have the IO error in the work we're going to do. But if you had several different kinds of errors you were expecting throughout your work, you just add them to the my error enum. So now, like before, we're just going to quickly read through the args and ignore the first arg. And we'll build a count W's function. This is actually going to count the number of W's in a file. That's the job of this function. So it's going to take a file name, and it is going to return a result of i32 or my error. So if it succeeds, there's going to be an i32, but if it fails for some reason, the result will be of type my error. So let's start with opening a file. So we use file open. We should probably import files. So that is in the standard library, standard fs for file system, then file. We'll also need standard IO. We'll get to that, why we need that in a minute. And we'll need standard env args. So when you use a let statement, even on a match, you need to end it with a semicolon. So now we've still got a problem. We just haven't handled every case of file open. So file open, like our function, returns a result. It could return the file handle, the mechanism for reading and writing to the file, or it could return a standard IO error. So in the case we get an OK, that value, I just want to put that value, I just want to accept that value and put it in F. So, but if we get an error, then we're not going to be able to count the W's inside a file that either doesn't exist or we couldn't get permission to open. So in this case, we're just going to return a new error of my error. So it's an enum, so we've got to specify which one, and that's E, because E is going to be a standard IO error, and that's what we're holding in our error. And so if this is if this has succeeded, F will now be the file handle. So now we're going to try and read from that file. So I'm going to create a string to read that file into. Let mute s equals string. We'll do if let error E. So only if this returns an error on F of read to string. Now read to string basically works. It takes a mutable pointer to a string, writes the contents of whatever reader it represents. In this case, it's a file, into that string. But normally this returns a result. The result will be OK and the number of bytes that it wrote, but it could return an error. So we have to handle that error, and in case we couldn't read the actual file into a string, we should return that error in some way. So in this case, we need to return an error, and it's got to match our error type. So we'll build a my error, and actually we can just pass up that E because it matches the right type. It is a standard IO error in read to string. It's complaining that the method doesn't exist. It's not that the method doesn't exist at all. It's that if you want to rely on a trait's abilities such as standard IO read, you actually have to have that trait in scope, that read, to be able to use the method that belongs to the trait. So now if we get to this point after that read to string, we know that we have successfully read the string, because if there was a problem, we would have returned already. Let mute res equals 0. Res I use just the variable I use for result. And then we're just going to loop through the string on characters for C in s.cars. Now it's kind of worth explaining that strings in Rust are organized using UTF-8. So some characters have different lengths. I'm not going to go into much more detail than that, but because some characters take up different numbers of bytes, you can't just read bytes one at a time and hope they match up on characters. String does have a bytes iterator and a cars iterator, and we want the cars iterator, and we're just going to loop through all the cars and check if they equal W. So if C equals W, then result plus equals 1. We'll just add 1 to the result, And finally, at the end of the function, if everything has worked correctly, we can return OK of result. Okay, so the only thing that's missing here is the main function isn't doing anything with the args. So what we'll tell it to do is we'll tell it to call count ws. So now we'll try let w equal count ws of, and that will be a, and a is a string. We take a pointer to a str, basically the same, and except that we do need to borrow the string to get that pointer. And then we'll just print out the name of the file and how many w's it has. So a is the name of the file, w is actually a result, so it could either be yes or no, and we need to just make sure that this result can be printed. So we need to derive debug for our result. IO error already implements debug, so that is perfectly usable. And then when we cargo run this, we'll cargo run this file with nothing, it just returns hello world. But if we give it the parameters of a file name, let's just use source main.rs. There you go, source.main.rs has OK 8W. So the function succeeded. Okay, and let's try it on a non-existent file, maybe source main without the .rs. And there's the error. But there are tricks we can use to make our count W's code nicer to read and slightly shorter. The first thing I want to do is I'm going to implement a trait called from IO error for my error. And the from trait requires a method called from, which takes the type it's coming from and returns the type it's coming into. So if we get an IO error, we should be able to return a my error. With that from, we'll take the E, which is an IO error, and we'll just put that E into the enum in the place where it fits. And so now that we have this from method, we don't need to return the my error of this kind of thing. We can use e.into, because when you implement a trait called from, it kind of automatically gives you a trait called into for the other type. This works really well if there are lots of different types of errors that you want to handle. So if for your error type you implement from for every error type you're expecting, then you can just call into whenever you get those errors, and that sorts it out. Or as you'll see in a second, question mark. And because this is an enum, you can just match through the enum to decide on your next action if that's what you want to do. A lot of times you just want to pass the error up the chain, which is what question mark does really well, and I'm going to show you now. So pubfun count ws2, so count w is 2, and again it will take a file name which is a str. It will return a result of i32, my error. But this time we're going to make the function a little bit shorter. So we'll start by declaring our string. Again, we still need a string to read the file into. And then we will open our file, and instead of matching on opening our file, we will just use a question mark. So this question mark does all of the work of match, and in an OK case pass it through, in an error case return it with the word into, because it depends on that from trait to make the errors work. And if that works, we can read it to the string s. Again, that's the string we've got to give it as there, and we put a question mark on here as well. So we've read the file, and with the file handle that we've got, we've read it to a string, and then we put a question mark on the end and semicolon. So that means if that fails, it will return as well. So 2 question marks in a single line. That's equivalent to having 2 of those match statements on one line. Then our return result will be s, the string, into a cars iterator, and then we'll just use one of those iterator functions, and this one's called fold. Fold starts with a 0, so that's the res in this case, and then it takes 2 parameters, n being the number we're building and c is the character in our current case. And then if c is equal to w, we add 1 to n, otherwise we just leave n alone. So again, this is just a simple closure, but that allows us to write fold on our iterator, so it builds an iterator that will perform the fold action. So that is 3 lines of code that does exactly the same as what the code above did. So using question mark in a result is really handy, and I just want to show that it does get the same result. Now I did want to just derive partial equality for the errors to just be able to assert that their equality matches, but standard IO error doesn't implement partial equality, so we couldn't do that. So I'm just going to do another match statement. If let OK A, OK B is equal to WW2, and we've got to wrap these both in tuples. Oh, sorry, and those are pointers because we don't want to actually consume them. Then we will assert equal A and B. So we just want to say that, so if we get the same thing and that they are, if they are both okay and they are both equal, we'll just print all okay. If they're both okay but they are different, we're going to get a panic. But if they're not okay, it's not even going to enter that branch. So it does print all okay. That means the result of calling both of those functions has returned the same result. So that is the end of chapter 1. In chapter 2, we are going to be looking at lifetimes, how pointers really work, how we can track memory, and the compiler makes sure that we don't do things with memory that we shouldn't be doing, and then have to get around the compiler a little bit. I will see you there.
Thank you for watching. Don't forget to subscribe to the channel. If you like the video, do give us a thumbs up and share it. Also check out amazing discounts and offers on our premium courses in the description below.